it coming through? Okay. Okay. We should get started so that we can launch more or less on time. All right. So what I'm going to be talking about now, in general, is recursion. So we saw a little bit of recursion yesterday, at least in the untyped lambda calculus. So if you just have terms or expressions of the lambda calculus and you don't bother with type checking whatsoever, you can start writing recursion, and we saw how that was encodable. But once you add types and you say, I only want to talk about programs that are well typed, then we lost that. And so let's dig a little bit more deeply into recursion, and we'll see how you can do that without, because it's nice to work in statically typed languages because they have properties like type safety and they prevent weird bugs from happening. Or Jan had the example about null pointers versus option types, that it just prevents this whole class of errors from happening when you hand off your program to the compiler. And that's a nice thing to have, right? So we want types, but clearly we also want recursion, right? So we started at the very beginning of yesterday with an extremely little language that had numbers and booleans, but it's very small. So for example, with booleans, we had the two constants true and false, and then an if-then-else construct. And that was not too bad, because if you use if-then-else, you can write down your own operations on booleans. For example, I might want an and or an or operator. I can use if-then-else to write that, and if you've done any programming, you've seen that before. But what about the situation with numbers? We had an addition operation, and well, we had a comparison operation, and that was it. What if I want multiplication? Do I have multiplication in that language? Can I write that just with plus? Well, maybe not in general. I would need some form of recursion or some form of looping in order to turn plus into multiplication. Right? That's the idea. And so in some sense, whereas the operations we had for booleans, the operations we could do on numbers were pretty limited. So I'm going to start by talking about, or thinking about, how can we do numbers in such a way that I have the tools that I need to write all sorts of interesting operations, and not just whatever primitives I happen to hand to you as a language designer, right? So what is a more general way of using numbers that somehow must involve looping intuitive, sort of expand or generalize from there. So for here, I'll start by considering just the number part of a language, right? So what's going to be our syntax of expressions? So our syntax of expressions E, what are those going to be? So they might have some other stuff, like they might have variables and functions, but just the number part, what's that? All right, so I'm going to include just two basic ways of building numbers, which is 0, I'm going to write it as Z, and the successor of a number. Right? So successor, so 0 is just the constant for 0, and successor is given me a number, I will give you the next bigger number, just that number plus 1. And so this way of writing numbers is sometimes referred to as piano numbers, or piano arithmetic. So who here has seen numbers before? Okay, so who is this new for that you've not seen the numbers broken down into 1 and plus? Okay, so a few people haven't seen that before, but the thing to think about is, can I write every number as some number of successors applied to 0? And it intuitively makes sense. So that's how we build them, and how are we going to use them? That's the trickier part. And so for that, I'll add what is referred to as the recursor. So it's a general sort of looping operation, which looks at the number and lets me do whatever I want by recursing. So the abstract syntax for that would look like this: rec of so rec of some number e. That's the thing I'm going to loop on. And the idea here of the recursor is it's just like primitive induction on numbers. And so here it's primitive recursion because it's about programming rather than proving, but really it's the same thing. And what do you do when you do induction, the most basic kind of induction on the natural numbers? I say, well, what's my base case? What if the number's 0? And then what's my inductive case? What happens if it's 1 plus something else? And so you do the same thing here. There's two cases you might have. In E0, which is what do I return if it happens to be 0? And then a E1, which is what do I return if it happens to be the successor of something. But when you do induction, when you do recursion, right, I don't just say, oh, if it's 1 plus something, here it is. Right? I expect to be told something. Right? So usually when I do an inductive proof, or if I write a recursive program, what two things do I learn in that plus 1 case? Usually you'll learn, okay, it's 1 plus what? What is it 1 bigger than? So that's going to be a variable that I'm given to me, right? So I'll be told in the plus 1 case it is x plus 1, right? So that's one thing, but that's the easy sort of thing. What's the hard thing is that inductive hypothesis, right? What is how the result if you had already done it for that case of x, right? So tell me what x is, you tell me what the result is on x, and then I'll tell you how to turn that into the result for x plus 1. That's the idea there. So it's just like proving in mathematics, but now we're writing it as a program. So this binds two variables, one of which is the body of the successor, and the other of which is somehow going to be that recursive result. We'll see in a little bit how we figure out what to put in for y there. Okay, so that's the abstract syntax tree. So the rec has two binders in this case, no binder in that case. And well, I find this particularly hard to read because it's very hard for me to remember what role x and y have. So it's much nicer to have more friendly syntax, so that's the one I'm going to be preferring. So the user-friendly syntax, it's the same thing, just written in a different way. It's going to be, so 0. Successor can just be successor, no problem there. But how would you write rec as something you might actually see in a programming language? Because no one so I'll write it like this: rec as, and what goes here, what you're doing is this is a lot like the case expression that Jan just told you about, right? What I do depends on what E looks like, so let's give two cases. And I'll write down the two patterns on what each case comes from. So rec on E, so look at E. If it's 0, then give back E0, right? That's just the base case. I don't really learn anything. I just have to say what it is. And then the recursive case is going to be successor of x with that recursive result y. And then I will give back the result in the successor case. So here, x is the contents. It's the number that is one less than the thing, or rather, e is equal to successor of x. And then y is just that extra variable that is my inductive hypothesis, or recursive result. Okay, so that's the syntax. And using that, let's look at a few examples on how you use this sort of thing to write some interesting programs, right? Or at least write some of the operations you might want in your language. So that's not addition, right? We had addition before. So can we use that to compute addition? Right, that's the question. So let's look at that. So first, let's just look at an intuitive definition of how you define addition when your numbers are always written as zero successor, and then how do you encode that using the recursor? Okay, so how would you write add if you were just doing this in a functional programming language? Well, you have two arguments. And how do we do this? Pattern matching, right? That's how you write a program in a functional programming language. So there's two possibilities. What happens if I add 0 to some number n? What is the result if I add 0 to n? It's n, of course, right? 0 plus anything is the same thing. Okay? And then what's the other case? So my first argument might be 0, but probably it won't be. So I've got another case to consider. Add successor of m to n. And what's that going to be? Right? And we want to make a little bit of progress. So if I'm adding 1 plus m to n, then the result should be 1 plus n plus m, right? We're just sort of switching that parenthesis around. So this is equal to successor of m. Okay. And then we might, ask ourselves, is this a good definition? Which, in terms of programming, or in terms of a program, means do I actually give back a result, or do I accidentally loop forever? So why am I making progress? So clearly this case is fine, because I don't recurse. Why is that recursion fine? Why is it okay to call add again, right? I tried to add something, and now I'm just calling myself again, so why don't I get stuck in an infinite loop? Why must it be the case that I always get an answer? It's because m is smaller, right? So every time I call add, the recursive call is one smaller on that first argument. Right? So that's why it makes sense. And that sort of informal justification on why my add function made sense. So for example, if I had written add successor of m n, that's kind of true in a specification sense that yes, if I add two things, it's the same as adding two things. But if I take that as a definition, it's totally useless because it's not making any progress. Okay?
If you write it the other way, add m and
Add m. Add m.
and sn.
Oh, yeah, you could also do that. Better is a big question. If you're writing in OCaml or Scheme, yeah. If you're writing it in Haskell, not really. In fact, usually that one would be better. So better for performance, I'm assuming. And it really has to do with semantics and issues of runtime. Right? So are you going to be taking advantage of something called tail call, which really cares if the recursive call is the last thing I do, or if you're doing something with laziness. So, that's a subtle issue. We're not quite getting into yet performance and how to write these things to be super efficient, but both would be correct. Here we're just looking for a correct function that gives and doesn't spin out forever. All right, so now let's look at how would you encode this? And that argument of, what's going on, and well, really, what are we doing? We're doing recursion or induction on m. And so writing it in terms of that makes that explicit. So how would I write this if I just had recursors and lambdas, right? Not this nice syntax. So, as a function, right? So add is a function of two arguments. That as two lambdas in a row. So what's the first argument? It's going to be some m, which is a nat, I'll say, right? So I'm given one natural number, I'm given another one. Lambda n is a nat. And then what do we do? Well, here I was matching on this first argument, so I'm going to do recursion on m. Okay? So we say rec m as And then 0, what's the case for 0? What happens if m was 0? I just give back n. N. And what happens if I have the other case, the interesting one, right? It's successor of something, successor of m prime, with the recursive result r. So what is the recursive result r? It's going to be this for the result of this for the next smaller m prime. Okay? And the goal here is in rec, but the reason why this isn't expression in our language is because add appears here and here. Right? So I can't just expand add and get the expression, because I would have to keep doing it. Every time I go to the right-hand side, I would have another call of add, and I'd have to keep doing that. Right? So I want to replace this recursive call of add with something else, and that something else is this r. Is it arranges to compute this on the next smaller m, and then gives it to you in the case that you might happen to want it. And so here, right, so it's successor of the recursive thing, so you would just write successor of r. Okay? Good? Any questions about that? Is that sort of clear what the game is? Okay. Let's do another example just to sort of see how this goes. So what about multiplication? Let's do that real quick. So multiplication, 0 times n is 0. Right? We know that from algebra. And then if I multiply successor of something with something else, what's that look like? Well, that's going to be n plus m times n. Right? So n plus mult m n. This makes sense because I only call multiply on a smaller m here. So that is getting me progress. And then you would like to, or you should convince yourself that yes, that definition is multiplication using your knowledge of algebra. And so now let's turn this system of recursive equations into an expression in this language. Okay? So it's a function of two arguments again. So we're going to start with two lambdas. Give me an m, which is going to be a natural number, and an n, which is also a natural number. And then what do we do? Right? So what are we matching on? The first or the second argument? What's that induction I'm doing? It's the first one again, because I happen to do it that way. So to encode it, you're going to recurse on m as, and what are the two cases? So what happens if the first argument is 0? Right? So you always say, what are these two possibilities? What if the first argument is 0? What do I get back? 0. Okay, and then what if it was successor of some m prime and the result of multiplying m prime and n happens to be r? So how can we say what that is without referring to multiplication explicitly again? What should that be? So what should I put here? Any ideas? Add? Did you say? Yeah. So add, or I should say add here because I didn't have addition, but it's the same. Well, I'll just leave this as n plus. So I should say add, right? So I want to add n, and I shouldn't say mult, so r, right? So I don't want to say multiplication, so I'm instead using this r because I'm trying to avoid explicit recursion in definitions and have the programming language do the recursion for me. That's the trick. Okay. One last trick. So in both of these, we didn't actually ever use prime. So what's that for? Why bother give you this other thing? Right. So here I used r. I ignored m prime. Here I used r. I ignored m prime. So that makes the predecessor easy to define. So what's the predecessor? What is the predecessor? That is the predecessor, and then you just match on the numbers. So there's two cases, predecessor of 0 and predecessor of successor of n. So what's, if this, right, what's the successor of, that's just n, right? And what's the number before 0? Just going to fake it and say 0. So this is predecessor, except when it's 0, then, you know, there's this extra thing. If you want to be really careful, you could use an option type to then say 0 has no predecessor, you get nothing. But that's, you can do that, it's perfectly fine. It's just a little bit more. And then so, how do we write this? The recursor is the only thing we can actually do with numbers. Right, so what is the encoding of this recursive equations into an expression? So we've got one number that we're given, n, which is a nat. And then what do we do with that number? We can only do one thing with that number, which is the recursor. So recurse on n as, and there's always those two cases with r. Right, so what happens if it's 0? Based on this definition, I get back 0. And what happens if I have successor of n prime? Based on this definition, what do I get back? N prime. And where do I have that n prime? It's given to me right here. Right. So if you want to just look into a number, that's what this part's for. You can look into it. And if you want to do recursion, that's what the R is for. Sometimes you want one, sometimes you want the other, so we have both. Okay? Good. So, yeah?
I find it a little confusing, like, how do we get n prime in evaluation of this?
So we'll see that. Yeah, so that's going to be when you define the dynamics, right? So just like with sums, in that case construct, the running a program is going to discover what that is and then plug it into the appropriate place. And we'll see that in 1 minute. I think first I'm going to do the statics, and then I'll get to exactly that, which is, okay, this is nice, but then how do you actually do it? Okay. So the types, the types of these things are nats, right? So the syntax of types, I'll write that up here. Tau is going to include maybe other stuff like functions, right? But here we're just focusing on the number part. Right? So this is sort of how do you add numbers to your language. Okay? And what are the rules going to be? So we should have one typing rule for each of those types of expressions. So there's a rule for when is it the case that, well, what is the type of 0? It's just a natural number, right? It's our basic natural number. And when do I know that's the case? All the time, right? I don't really need any other justification. 0 is a natural number by definition, right? Okay. So what about the successor of something? So what is the successor of E? What should that be? Right? So it's taking a number and adding 1 to it. So it should be another natural number. Is it always a natural number? Well, assuming that I'm actually giving it a natural number, if I give it something else like a Boolean, what's the successor of true? I don't know what the successor of true is. That doesn't really make sense. So it is a natural number, assuming I gave it a sensible argument. So assuming E is a nat. Okay, so those are the easy cases. What about rec? What about the recursor? So that's the hairy one because there's a bunch of moving parts, right? So let's look at that. So rec. So what happens if I've got this? E0 and S of x with y goes to E1. Okay, so what kind of output should I expect from the recursor? Maybe it's an at, but maybe like is 0, which would have the type of nat to bool if I had bools in that language, right? Might I want to write such a function? Or the less than would I want that kind of thing? Probably. If I had bools, I'd like to say that, yeah?
Does E0 and E1 have to have the same type?
Yeah.
And so whatever that shared type is the result.
Yeah, so we're kind of getting into that, right? So it's the result could hypothetically be anything, and I'd really want that because I want to define predicates on numbers, and I want maybe to convert a number to a string and all sorts of interesting stuff. But for it to make sense, they should be the same, right? Because without running the program, I don't know which one I'll run, which means they have to be the same for me to predict before running what they are. So this is a lot like the case. I kind of said, oh, it's kind of like the case. It's actually extremely like the case statement for sums because, well, numbers are a lot like a sum plus a bit of recursion. And so this is, well, we'll see, these are the like left and right, or the two possibilities, and then this is like the case with the recursion. So then the output type tau is going to be, right, we said the shared type. Somehow both of these should be of type. So then a recursor has a type tau under which conditions. So can E be anything at all? What should E be for this to make sense without crashing? It should be a number, because I'm really only going to say what to do if it's your successor. So E can't be whatever you want. This part here has got to be a number, so I know which branch to take. It's got to be 0 or successor. So E should be a nat. Right? That's the first part. I'm recursing a number. And then we now have the two branches on what to do. So what's E0 going to be? It's got to be a tau. Why does E0 have to be a tau? Yeah, because that might be one of the results of this. And we're expecting a tau out of it. So E0. Or otherwise I'd be in trouble. And then, what about E1? What should E1 be? So also a tau. But we've introduced two variables here, right? This binds two variables in E1. And so we should include them in the environment because E1 gets to see two new variables that weren't around in its scope. So I've got an x and I've got a y. Yeah, that should clearly be a nat. Why is that? Because, well, it's going to be the previous number, so it should be a number. And what about y? What should y be? Tau? Yeah, so that's the tricky part. It should be tau. Why? Because it is the result, which is a tau, of the previous case. Okay? So that's the typing rules for numbers. And so these are the two introduction rules because they tell you how to make numbers. So I've got a starting one, and then I can make a bigger one, and then this is the elimination form. Because I'm given a number, and this is how you use it. Right? Okay, good. And then what's next? I'll do the dynamic sum of value, of course. Why shouldn't it be a value? And the right, so that's what makes this one lazy, in contrast with the eager products and sums from before, which said it's only a value if the component's a value. So this is one of the differences. Okay? So those are both values, and those are the only values that have to do with numbers. Right? If you had lambdas and functions before, those would also be values still. Right? So that holds true. And let's look now at the main reduction rule for this. That's the main thing. Right? So what are the resolves? How do I resolve the recursion? So one possibility is if I'm recursing and I'm getting 0, it doesn't seem too bad as z goes to e0 and successor of x with y goes to e1. So that doesn't seem too bad. What do I do here? Easy. E0. Okay. No problem. What about the interesting case? What happens if I'm given successor of some e as z goes to e0 and successor of x with y goes to e1? What do I do here? So this is, again, a lot like the case for sums, and also kind of like the case for functions. And anytime you've got one of these binders, right, clearly the result should somehow be e1, but it's got references to x and y, and I have to put in something for those. Right? I should actually say what x and y ought to be, and then run e1. Right? So what I'm going to get out is e1 and some substitution for x and for y. So that those don't somehow leak and become free variables, I should instantiate them. So what should x be? That should be e. That's the easier one, right? It's just that number, right? We're just matching, right? S of x matches with S of e as long as x is the basic part. So we've got e for x. But what about y? That's the tricky part, right? That's not just e, that's something else. I kept saying that's the recursive results. What was that? Recursive e. Yeah, so that's the idea. It's this whole thing exactly again, except e here instead. Right? What is the recursive result? It is this if we had put e there. Right? And so that's exactly what you do. You just say, well, you put together a new recursive expression where now we're on that previous step. And we do exactly the same thing, right? Our response isn't any different. We just want to see what that response is on e. And then this goes in for y. Okay? We sort of see. So this is the complicated part. Sort of see what's going on. If the recursion works out, this is the previous one, and that should go in for y. Question?
You're putting in e for x, right?
Oh, thank you. Yes, e for x, not y. E is for x because that comes from there. Yes, thank you. Okay, any other questions? Okay. So that's the basic sort of. This is the reason why I made it call by name instead of call by value. So in call by value, you should only be plugging in values for variables, and this very clearly is not. So that doesn't really make sense in a direct sort of way. But if you're doing call by name or a lazier style of evaluation, that's fine. I can plug in any expression I want for a variable, and that's what we're expecting. You can do this for call by value, but you'd have to kind of rearrange it a little bit to avoid this problem. but it's essentially the same thing. I did call by name because it's a bit easier here. You can just plug in the recursive result without having or something like that. Okay? Any questions? To finish off, you have to also say those rules of when do you evaluate sub-expressions, right? And like I said, there was the two different ways. So I'll start by describing some evaluation context, but then give the rules explicitly. Where should I try to evaluate one of these things in which number? It should be here because I don't know how to recurse unless I've got one for real. So I should try to evaluate it to get it because this might not be Z or successor. It might be the addition of two things. It's neither case. So I should evaluate that addition to figure out whether or not it's 0. Right? So one of the evaluation contexts should be this thing, which is when you see the recursor, evaluate this part because I need to know which case to take. And in general, when you see anything that looks like a case expression of any sort, you're going to have to evaluate the thing you're discriminating. It's the same with if then else as well, right? To know which branch to take, I need to get the Boolean. And let's see, expanding that out, the extra rule you need looks like this. It looks like if I've got rec E as Z goes to E0, successor of X with Y goes to E1, that can take a step to rec E prime as Z goes to E0 and successor of X with Y goes to E1 as long as E takes a step to E prime. So that's the implication of that. Okay? Question?
So right now, I mean, these two are just floating judgments.
Yes. So if you want to see them as judgments, it's an axiom.
Okay.
Yeah.
So these are all, I mean, but
those are axioms.
Those are axioms. But this one on the bottom left, doesn't it need E to be a val in order for suck E to be a val?
Not for lazy, right? So that's the difference. For eager, you would say E needs to be a value for successor of E to be a value. This is the eager version. Eager, and then this is the lazy version. And I chose lazy because I knew that was coming. And this makes perfect sense in a lazy language. This is extremely questionable in a eager language. And I wanted to keep this to the simplest possible form. It's not that you can't recurse in an eager language. It just is a little bit more bureaucracy. So I did this one. But if you want eager numbers, which is a extremely sensible thing to have because they correspond exactly to the natural numbers, and there's some extra nicety fits, but then the recursor is worse. In the lazy version, the recursor is great and what you want, but then you don't know essentially that if I have a value of a number type, I would like a value of a number type to be successor of 0, right, n times, right? There should be n applications of successor to a 0, right? You might write this as successor n of 0, and the n is the number it represents. And so in the eager semantics, you get that because, well, 0 is a value, and successor of a value is a value, so the only thing it could be, if it's well typed, is this. In lazy, I can have successor of, well, I don't know, whatever, and that's a value, and it's not simplified yet. And that's like if you were to write in Haskell, you could write an infinite series of successors, just like you have infinite lists, and so that doesn't really correspond to a natural number. So that's a consequence of this decision. And one of the more broad lessons is what you do is up to you, right? It's whatever suits your needs, but there's consequences to every decision you make. So it's not as much a matter of right or wrong, and if you do it this way, you're wrong and you should feel bad about it. It's just, well, if you do it this way, this is what happens. And maybe you're okay with the consequence, maybe you're not. Do you have a question?
Yeah, so this may be related to what was just asked, but the adding that additional evaluation context.
This one, or that rule? Same thing? Yeah.
So though, is that when you want this to be eager?
You want that no matter what. Because for this to go anywhere, I've got to have a successor or 0 here. So I need to evaluate it. The extra rule you would need for call by value would be this one. If you want to eager one, you would say that evaluate inside of a successor to get that to be a value. So that's the extra bit. So you'd have another rule here which says E goes to E prime, means that successor of E goes to E prime. And so this is your call by value addition, and then this corresponds here to this. This is a call by value addition. So that's how you get a call by value semantics, and then these rules would be restricted. So that this would have to be a value, and well, somehow you arrange that I'm not plugging a recursor in for y, because that certainly is not a value. Yeah.
So you need that transition rule.
Yeah.
Because both of your axioms are
Yeah. So that's the general pattern. If you want to go from call by name to call by value, you're going to have extra evaluation context, aka you'll have extras of these sorts of inference rules to evaluate in more places, because your base case axiom reductions, the things that really do the work, are weaker. Right? So I'll be able to apply this rule less often, so now I have to compensate for that somewhere else, because I don't want to get stuck. Right? I want to keep going, and if I'm not willing to make this reduction now, then I better reduce E until I'm willing to make it. Right? Right, yeah?
Why do we have these two different types of lazy evaluation and eager evaluation? Like, what is the benefit of
So why do we have them? So, well, in one sense, we have them because both are possible. Right? There are two different ways of doing them, but then the broader question is, okay, fine, but when would I use one or the other? Right? So in practice, the two big ways you see those difference is, on one hand, the ML family of languages that includes OCaml and F# and all sorts of things now. And those are all eager. On the other hand, you really only have Haskell as a lazy functional language. And there's ramifications of that, right? There's pluses and minuses. And at the end of the day, you usually want some amount of eagerness and some amount of laziness to get real programming done. But the general sorts of differences is that in eager, it's much easier to make an estimation of the cost and performance of something without just running and profiling it. So it's much easier to do a cost semantics, which we're going to do later in the week, which is look at this program and estimate how expensive it is to run. What's the cost of it? That's pretty straightforward to do for an eager language, pretty hard to do for a lazy language, in that I don't know that anyone's even done that yet. But it certainly exists for an eager language. So that's one point in favor of eager, is that it's easier to know the cost of things. Laziness, one of the big advantages are being able to break things down and compose programs in a reasonable way. So a good paper to read on that is why it's not really, it's a nice name but not really appropriate, why functional programming matters, by John Hughes. U-G-H, I don't know if I spelled that right, but apology to Hughes if I've typoed it. So really this should be why lazy functional programming matters, because that's the real point, is if you've got laziness, you can do some really neat things which involve taking a large problem and decomposing it into tiny parts and then composing it back together and have it work. So that doesn't work in an eager setting, but it does for lazy, yeah?
I've never programmed in Haskell,
Yeah.
and I don't know anything
Yes.
about lazy. So I'm looking for one use case where eager won't be good enough, but lazy is like
So that paper is full of them. That's why I pointed out. There's a bunch of practical ones like, oh, we want to compute the numeric derivative of something, or we want to write an AI for tic-tac-toe or chess. All sorts of practical examples where he really uses laziness to write the program. And if you just took his code and transliterated it into OCaml, it wouldn't work at all. It just doesn't make sense. So that's where you use it for something useful. So that's more about being able to compose functions and have them only compute what's needed, right? So I can decompose and not go way out of my way to compute things that are needed, and that can be used for practical things, whereas eager is great for performance. It really lets you get a handle on that, and laziness is kind of notoriously complicated for performance. Yeah. Was there another question? That was it. Does that answer the question? Yeah. But that's a really nice paper to read. You don't really need to know Haskell for it. He introduces some things gradually. Okay. Okay, so that's numbers, right? So now we've looked at, in general, if you want to add numbers to your language, that's a good way to do it because for the cost of one maybe slightly complicated eliminator, I get lots and lots and lots of functions. I don't have to add every single primitive function that I might want on a calculator, or I might want on in my language to it. It's like the difference between a 4-function calculator that can do 4 things versus an Intel machine that can do everything. Right? Clearly one is much more nice than the other. So that's good. Downside though, what? Well, okay, I did this for numbers, but numbers aren't the only thing, right? Programmers don't just write programs on numbers. We have all sorts of stuff like lists and trees and all sorts of data structures. And I've just shown you how numbers worked. So if I want lists, oh, well, I'd have to do like the same sort of thing, but for lists. And if I want trees, I'd do the same sort of thing, but for trees. And that gets awfully tedious. So a way around that is to say, okay, this is a recursive type. And it's recursive because of this sort of thing. A natural number expression can contain more natural numbers, right? That's part of the type. But how can I do recursive types in a more general, right? What is a formula for doing recursive types? So that's what I'll look at now. Okay. So I'm going to look at recursive types more generally. Oh yeah, and I think I said before as a note that this corresponds to primitive recursion. So anything you could define by primitive recursion, you could define like this. But that's not everything. And then so one of the consequences is that sort of intuitively, right? There's no way to write an infinite loop because this always goes down. I've only let you written programs that will terminate. So we're doing recursion, but we still have termination. Okay. Now, how to do this more generally? I'll write a recursive type, or a recursive type former. So now, whatever other types I happen to have, the recursive type, I will write like this, mu alpha dot tau. And so alpha is a type variable, and tau is another type, and this is a binder for that, right? I use the period, so this is saying tau might refer to alpha, and this binds that alpha. And the idea here is this isn't polymorphism, even though it's a type variable. This is type recursion. So what does that mean? There's a couple different ways, there's a couple different meanings you could have. And so one way is known as equirecursive, where the idea is that it is equal to. That when I say mu alpha dot tau, I mean that that's the same thing as tau, where for alpha I plug in the same thing. Right, so I'll plug in mu alpha dot tau for alpha. So that's equirecursion because the two are the same type. Okay? And that certainly gives you recursive types, but it's a little bit difficult to deal with. So what you see in practice is called iso-recursive, which is except you weaken this to say it's iso. Okay, so that's mu alpha tau for alpha, which means that I can convert between things, but that conversion is explicit and voiced in the program. Right? It's not that these types are identical, it's that they are convertible between one another. And so that means I ought to have some operations for going between these two sides, right? The recursive type and then the unfolding of that recursive type. Okay? So what do those look like? Well, common names for those are going to be folds of some E and unfolds of some E, where fold goes this way and unfold goes that way. Okay, right? So fold goes from, well, unfold takes a recursive type. Fold. And that's what's going on there. What are the types for this? So there's actually, no. Okay, yeah. So what are the types? So what's the type of fold? What's the type of unfold? Right? So let's look at those rules. Fold. Fold E, right? Look like. So what should the type be? I said here fold goes this way. Given something like that, it gives me the recursive type mu alpha dot t. So that means the type of a fold should be some sort of mu alpha dot t. Under what assumption? So what's E have to be for this to make sense? That has to be, E has to be tau with mu alpha dot t for alpha. Because I'm going from the right to the left in that isomorphism there. And then what about unfold? So similar. I've got an unfold. Unfold. E. That looks like, well, so unfold goes the other way. So E should be one of those recursive type things. Okay. It should be a mu alpha dot tau, and it's just sort of flipped from fold, right? What I get out is tau if you were to plug in that same recursive type for alpha. Okay? And so this is the introduction form because it builds a recursive type. This is the elimination form because it does something with that recursive type. Yeah.
So is alpha a free variable?
Is a free variable in tau, which means that also I've got some type variables in the syntax of types, not just constants, which are primitive types, but a true variable. The detail here, though, is that at least just with recursive types, you can say all types should be closed. Right? So when I'm type checking a term, that should be closed. And is this property preserved by the rules? Right? So if this is closed, that means the only free variable, type variable in tau could have been alpha for this to be closed. And I've plugged in something for that alpha here, so this whole thing is closed. Right? And then vice versa here as well. So that's a trick you can kind of have. Yeah, there are type variables, but they only show up when I've got a corresponding mu, and you don't have to deal with the extra bureaucracy of figuring out what type variables are allowed. It's really just none, except in a recursive type. Yeah?
How important is like the equity versus iso recursive type? Do you really understand kind of what
So different. So Let's see if I can remember exactly. So here, something like type checking is not that hard because the folds and unfolds tell you exactly where to do this conversion. If I have equi-recursive, I don't know where to do that. And so it can be really hard to figure out what is the type of something. I'm not actually sure that type checking, or at least type inference, is decidable. But here, if you want those, if you want decidable, or like every term I can immediately read out type, we can add, remember we had those annotations on various constructors and things. I could say alpha.tau here as this extra annotation, alpha.tau here, and then it would just match. Right, so that's just what it would have to be, alpha.tau e, and then here, unfold, alpha.tau e, right? So that's the really explicitly typed version, and I can just read off the type from it. I don't even, I know what that ought to be because, well, it's a fold of this, so it's got to be a mu of that. And here, same thing, right? An unfold of that, so it's got to be the substitution form, right? Plug in the recursive type for it. So this makes lining up types with expression really easy. Equi-recursive, that information is completely gone, and it's not easy to recover. So that's a consequence, and that's why it's much easier in practice. Much easier in practice, and in fact, in practice, you have more or less that. So functional programming languages, it's not that they're built in, you could easily define them yourself, right? And whenever you define a recursive thing like a list, it's essentially a special case of one of those. And that's what I'll look at now, which is some examples of how you can use these general recursive types in order to encode some specific ones. So the first case to consider, of course, would be natural numbers, because we had just looked at those. And see, can I represent natural numbers using these recursive types? Let me finish the dynamics real quick. So what should that be? So I'll first do the call by name because it's fairly short for both of them. So what are the rules for running fold and unfold? And right, they just go back and forth. They just undo each other. So if I have an unfold of a fold, well, if I have an unfold of a fold, then that just goes to E. And what else? Well, I'll need to say that if I want to unfold something, unfold E, unfold E, unfold E goes to unfold if E goes to E prime, and that's all I need. Okay, and then as a note, and this is somewhat related to, in the lambda calculus, I said there were 3 rules, right? Alpha, beta, and then eta, right? Where beta we use to run programs, but eta was just, in general, sort of property about programs. It's not used to evaluate them. So here there's a corresponding eta law, which is, the eta law is the other direction, right? So running a program, you unfold a fold, but it's also true that a fold of an unfold of some E should be eta equivalent to that E, as long as it is some sort of recursive type. So I wrote something like that for lambda, right? Where the beta rule was, what if you apply a lambda abstraction? And this one, which is, so that's the beta, and then the eta is what if you abstract over an application. And so here's what if you unfold a fold is the reduction. And what if you fold back up and unfold? That's just a property of programs. So let's call by name. And then what are the values? Well, here the value would just be that fold of E is a value. And this also is an axiom. Question?
So the fold always have to be measured by a fold?
Well, if you want the contents, that's sort of give me what's inside. Right. So I could just return a fold. And that'll happen. It just is a value. Yeah, so to do something with it, you've got to unfold it first if you want to do something interesting. But if you return a value of a recursive type as the result of something, it could just be a fold. And then that would be it. And then if you want to use that in the future, you unfold it. And then how do we modify that for eager evaluation? Well, right, so first thing is that we're more picky about what values are. It doesn't just start with a fold, but it continues to be a value. That's that main is that fold of E is a value only when E is a value. And then the mapping thing is that we're going to be picky when we run one of these base reductions. So I'll only unfold a fold. I only get E if. Right. So I only call a function when I've got a value. I only unfold it. That's a value, which means I've still got that same evaluate inside of an unfold, which is necessary to keep going without getting stuck. But then there's also this extra. If I've got a fold of something, I should at least try to evaluate it so that I can eventually run that rule. So E goes to E prime. So this is call by value, and then the plus the other one up above. Right. Yep.
On the very top, is that, of the other panel, all the way to the top? That's not a premise, that's its own axiom right up there.
Yeah, that's a separate thing.
Yeah, okay.
Yeah. Separate thing. Yeah.
And then is that one right below that also, the unfold fold?
Yeah.
That's also eta?
Other way around. So this one, if you want to make the connection, this is like the beta law from the lambda calculus. How do I reduce something? And this is a property. This is an extensionality property. And so you don't use extensionality to run programs, right? Beta-ish stuff is the engine of your language that gets work done. And this would be used by a compiler or you to figure out what code does. Can I write it in a different way? Maybe optimize it, maybe prove something about it.
Okay,
Yeah.
since fold is right from that, that's why it's...
Yeah, and so that's the idea, is if I've got one, and the other way you can think about it, especially here, is I've got a fold value. Now I want to do something with it, and I can't do something with it because it's just a mu. So if somehow this contains stuff, I want access to that stuff. So unfold is give me the stuff inside. And so unpacking that is really the action that's going on there. And saying that, oh, I could unpack something and then repack it back up in a new wrapper. And that doesn't change anything. That's just a property. That's not something you need to do to compute. So let's look at, so how do you recover some recursive types, specific ones, from this very general one? So what about nats? Right, so nat was, from before, nat was a type with two cases, right? I either had 0 or successor of another nat. So I could represent that product type. So I could say that nat is isomorphic to a unit plus a nat, right? Where the left-hand side tells me I've got 0, and the right-hand side tells me I've got 1 plus whatever that is. right? And if those two are isomorphic, that's another way, or that is an isomorphism of this type. You can always convert a natural number into a sum type like this by just checking are you 0 or not and putting it in the left or right. And if I've got one of these, I can do a case. If I've got the left or right, I either return 0 or hit it with the successor. Okay? And so remember, we had that isomorphism there. So the whole goal, just like when we wanted to get rid of, when writing programs, I don't want to have the same defined name appear on the right and left-hand sides, because that's not a complete definition, right? It's circular, but maybe in a meaningful sense. So how do you get rid of circularity? And that's what mu is for. So nat 2 could be alpha unit plus alpha. Alpha is the recursive occurrence of the data type nat, and I'm just kind of binding that up as a single thing. So whenever I see the recursive occurrence of nat, just write alpha here, and then that's what that is. And then be written using the sum types that you just saw an hour or so ago. So 0 would then be defined as, well, let's see, does this make sense? So is L dot unit. What's the type of that? This is unit plus a type A. But that's not one of these things. I need to fold it up. So that is to say I've got a value of this type nat. I'm packaging up the contents. And then it's a cluster. Sum E is the right-hand side of that E, right? So the right in the right constructor, and then that just looks like something to the right. So does that make sense? So that's natural numbers. So you didn't really need to define at least the constructor part, the introductions, because you could define that in terms of recursive types. And you need the recursion because the successor, one of the operations of the type, refers again to that same type, right? Successor is a function from nat to nat, not from some other thing, bool-the-nat or something. Okay? Now let's look at another example. What about list? So a list of elements tau. How would you write that? So a list, a value of this type is going to look like, well, it's either empty or it's a construction of a first tau and then the rest of the elements. That's the common way of representing lists in functional programming languages is the empty case or a list of the first element and then the rest. And you would write that as a list is isomorphic to either a unit, which is the case for an empty list, or a pair of a tau and another list. Okay. List of taus. So a list is equivalent to, or as isomorphic to those things, which means we can write it as a instance of a recursive type using mu alpha. List of tau is then unit, because that doesn't refer to the recursive part, plus tau is just tau. And then I don't want to write the same thing here, so I use alpha. Right? And then so the nil, the empty list constructor, then looks pretty much just like 0 because it's about the same thing. Fold L of unit. And then what about cons? What if I have an element E and the rest of the lists E prime? How do I represent that? So that's going to be the right case. It's right here, right, in either one. So we've got on the right, I've got a pair of E and E prime. All right, so that so far matches this, except that I've got to fold it up. So fold that. Okay. Good, and then you can do binary trees and all sorts of other things. That's my question. So I'm going to get to that in a second. So how do you use unfold? So the one case, write a case on nats using unfold. So if I just want to say what to do in 0 and what to do in successor, but without the recursion stuff, I could say that case some e of 0 goes to e0, and successor of x goes to e1. So it's like recursion without the recursion. And so how would that be defined? So then you would say case unfold of e of in the left, I just have some boring unit value that I don't need, and I give back E0. And in the right, I've got the actual natural number x, and then I give back E1. So if you want to just do case on numbers, you would have to unfold it first to see the sum type. Right? This isn't a sum type, this is a recursive type, which is different than what's underneath. So unfold is give me what's inside. Okay? But case is not the recursor. It's a lot more boring than the recursor. The recursor does a lot more stuff. And so I'll finish now by showing again that something sneaked into my language without me trying, which is for better or worse. I don't need that anymore. So remember, we had the simply typed, well, we had the untyped lambda calculus. I could do any recursion and loop forever. And then we added types, and that goes away. Every single expression will finish eventually. And then here we added products and sums today, and then even natural numbers, which has some sort of recursion, but all of those language extensions preserve the termination property of the simply typed lambda calculus. So does this have the termination property that every expression will finish eventually? So who votes for, yeah, of course it's still got that. I didn't add recursion. It's still typed. Who votes for no? Maybe I've given it away by bringing up the topic, because it'd be boring if the answer was sure. But yeah, so I didn't add recursion, and it's still typed, and yet I'm going to have loops in the language. So let me look it up, because it's a little bit tricky. But here we go. So the real thing was that the recursion, right, we had, I'll write it this way. Before, we had essentially a self-application, lambda x, and then x applied to x, and then omega, it was equal to, big omega was equal to little omega applied to little omega. So that's just breaking it down a little bit. We had that, and then omega took a step to omega, or rather, right, it loops back around. It steps to itself, so it just keeps going without making progress. It turns out that by adding these recursive types, right, so simple types got rid of self-application because there was no type that I could apply it to itself, but now there is, right? And the trick is that you're essentially abstracting over being recursive about the input, right? So the type alpha arrow tau, okay? And then what's the type of this x? So the type of the x is then going to be a mu alpha, alpha arrow tau. That's the type of the parameter, of course, because that's the left-hand side of... oh, I don't need that parenthesis out there. And then, what can I do? Unfold x, that's now a function taking the type of x as an input and returning tau. So unfold x. This has the type mu alpha, alpha arrow tau, 2 tau. That's what unfold does. It just replaces alpha with the whole thing, and that's what that replacement looks like. And now, that's something I can apply to x. So I've snuck back in a self-application. And the real death knell is this one, which is, can I reapply self-application? Omega, big omega, is type tau. And what's that going to be equal to? Well, I want to apply this, which is a function, to something, some value that has that type. And what has that type? Well, if I fold it up, if I fold omega up, what's the type of omega, or fold of omega here? Right, it's go backwards. We saw that this goes here via unfold, right? So this is unfold. Writing it out, mu alpha, alpha arrow tau, 2 tau is isomorphic to mu alpha, alpha arrow tau. And so this way is unfold, and this way is fold. Okay, so then this is a mu alpha, alpha arrow tau. So it type checks. So recursion in types gave me recursion in programs somehow. I didn't have recursion in programs. Isn't that a bit odd? Okay, so omega is not all that useful because, right? But you can do the useful form, which was that Y combinator we saw before. And what's the type of the Y combinator going to be? The idea is you give it a function on some stuff tau, right? And it will find you the input or the value such that when you feed it to Y, it's the same thing again, right? So it takes a function that modifies a tau and gives you back a fixed point tau. Okay? So how do we write that? And this one gets a little bit hairy because you've got folds and unfolds in the way, but it's essentially the same definition. You just put a fold and an unfold in the right place to placate the type checker, basically. But it's the same program. Okay, so what do? It's give me a lambda x, which is going to be one of these things. Give me lambda x, which has the type mu alpha, alpha arrow tau. And then I will call f on unfold x, x. Right, so that type checked for the same reason that this type checked. I just put an f in the middle. And then what else? So I want to apply this to itself. What is the type of this function? It's this 2 tau, which is exactly the same type as little omega here. So to apply it to itself, I just need to fold up the argument, which then compresses back down the type. So here you have fold of lambda x mu alpha, alpha arrow tau, and then f applied to unfold x applied to x. Okay, so it's the same thing that I just put an f around the self-application. So it might be useful instead of completely useless. So that sort of story of, oh, well, we had something we didn't want, which was infinite loops, and we got rid of them with types. That's great. And then now I want lots of types because they're useful, and I want to manipulate lots of types of things. But then it snuck back in. So you have to be really careful when you're doing these sorts of extensions. If you really want the property that every program terminates, it's an easy one to break. It's hard to maintain. And even like innocuous things of like, oh, well, I can fold and unfold types, whatever. That gives recursion. So wrap up the discussion of recursion there, unless there's any questions. Yeah.
We have their lambda. So down here at this
Yes.
stage, there's the lambda is the expression that the lambda f finds, but the fold is the input.
Yeah.
To
Well, yeah. So x is going to be bound to this, which
x is bound to that.
Yeah, the whole thing.
But what's f bound to? So what's
F is just some input to y.
Oh, it's some input.
So you say y of f, and that's just f.
Yeah,
F doesn't really
that's
matter. That's kind of, and you kind of know f mostly is that that's what f.
That's the thing that we apply to y.
Yeah, exactly. Be the case that y of f, and it's going to take a few more steps now because you have to unfold it. So it's the same kind of trace as before, but you plug in this whole thing, right? And just like here, right? How does this work? So you plug in full little omega in for x here. Unfold, right? So to expand this out, ignoring the f part, right, omega, big omega is little omega fold omega. That takes a step to unfold a fold of little omega applied to fold of little omega. Fold of little omega. Why is that? Well, I just plugged in fold of omega for x. That's all I did there. And then this is where the unfold of fold rule happens. Right? So you use all of the rules to find the root x. This is what actually reduces, and you get back omega applied to fold of omega. And that's where you started. So it takes two steps now, because you do a beta reduction of a function, and then you unfold the fold, and you're back where you started. And so y is just like that, except that there'll be an f out here. Right? So y in two steps goes to f, well, almost. I'll say it's equal to f, y of f, the annoying detail that the f has already been embedded on the right-hand side, but aside from that, it's the fixed point again. And you don't even see from the outside the fact that I use fold and unfold. That's just a detail. Yeah?
Two more small things. Unfold xx, we associate to the y.
Yeah. I kind of was lazy about writing the association, but that's...
Unfold x returns a function which, you can plug x into that function.
Yeah.
And then
I would be asked, is beta reduction kind of isomorphic to step?
Two-step.
yeah,
Meaning?
meaning like when we take a step, we beta reduce.
Oh, yeah. So
Like a
this...
dynamic semantic.
Yeah, so the step of a function
Yeah,
in the dynamic semantics is the beta law.
right.
That's what it is, right? That's the main step, and everything else is finding out exactly where you apply that main step. And so the beta law from the way old lambda calculus from the 1930s is the reduction that when I call a function with an argument and I know what the function is, I can substitute. That is the beta law, and we're just using that as part of the dynamic semantics in order to run programs, which is why I call it that engine of programming languages, right? It's how you run them. And then you have other sorts of laws that are more or less the same sort of thing. Like here was if I ask for this or that, right? those are the main steps that you're doing. And then the rest of the dynamic semantics is how do I find out where, in some unambiguous and deterministic way, where do I apply those rules? So other ways of describing programming languages might not care about deterministic applying the rule in exactly one spot for any particular problem. So there's also reduction theories and equational theories, which say you can apply the rules more generally and you have some more flexibility, but that's a little bit different from an implementation. And it will always do one thing because computers are mostly deterministic unless you're doing some concurrency sort of thing, right? But like sequential programming is deterministic, and this is all sequential programming stuff. And when you get into the concurrency part, then you'll see more essential non-determinism. It's not just, well, I can pick where I do stuff, but no, there really is two fundamentally different and non-overlapping things to do, and you make that choice, right? So that's a different sort of thing. All right, any other questions? I think that's it. I'll let everyone go to lunch. And we'll meet back here at 2 and continue on.